Okay, so today we will learn a new topic that is what we call topological sort. Okay? It's a sorting algorithm, but it requires an advanced algorithm that you learn in the graph theory. And so let's see what is the problem we are solving here. So let me share with you a screen. All right, so here is an example from the real life. So suppose that we have to dress up, right? So that says we have to put on the socks, the short, the pants, the belt, the shoes, the shirt, the tie, and a watch, for example, right? So for adults, usually we just dress it up and it looks like we have no problem at all, right? However, if we have to teach a small kid, not sure if you have a small sister or brother, or I mean, if you have a kid or not, I guess not. Then when you watch them to dress up, you sometimes it's very funny, right? So they may put on the shoes before realizing that they have to take them out because they forgot to put the pants on before that, right? So how can we have an, let's say, a list of items that we can tell the kids that, okay, you just follow this list, then you will be fine, right? So it's what we call the topological sort. So we have a list of items with interconnections between them, in that one has to be executed after the others. And we just want to have a list of items in one line. For example, we can tell the kids that do the following thing. So first, put on the pants, right? I mean, we can tell them many different ways. It depends on the patterns, right? So we can tell them that, okay, put on the pants. Then after that, put on something else, right? Okay. It may not work because we still need to have the short and the sock, right? So the question is, how can we find a list that will help the kids, that if they just remember that, or if they just follow that order, they will be fine. Okay. So for example, what we can do is as follow. Not sure if I have the things here. Okay. So I don't want to run the algorithm right now because we need to be reminded about something. Okay, so for example, we can say the following thing: we put on the shirts, right? And then looks like I'm out. And then after that, we tell them that to put on the socks, and then the short, and then the pants, right? And then after that, the shoes, and the belt, and then the tie and the watch. Or we can have watch and tie. Okay. So for example, we can tell them that here is the list of items. You just put shirt, socks, short pants, etc. And you will be fine without violating any rules. For example, have to have socks first before the short, right? So, for example, we can tell them here, and based upon this list, we can go back and check the uh, constraints we have. Okay, for example, whether or not we have any violation of the constraints. For example, the constraint between socks and short. Okay, sock and short. We have socks before short. We are fine with that, right? So similarly, you can check on other constraints like shirt before tie. We have tie here and shirt before that, right? So that is what we have as a solution. Okay, so it's a problem. The problem sounds like that, right? Okay, so let me give you one more example about another example, another application in our real life. That is about how to advise the students to take the courses. So remember that courses you are taking for your degree has a lot of prerequisites, right? Prerequisite means that you have to take the prereqs before you can take that course. So that means we have a bunch of constraints. So here is one example for that we have is you have to take the course 143 before 311. Okay, so this one is an arbitrary graph. I can build up a graph for our computer science program a little bit later. Okay, maybe I will spend a little bit time for writing that out. Okay, so that said, here is the list of courses with prereqs. And how can we tell the student that you have to take this course for your freshman, right? First semester, freshman year, here are the courses you should take. And then similarly for your sophomore and then junior and senior years. How can we know that, right? So that said, we need to find a list of courses so the students can take one after the other semesters and don't have to worry about the prereqs, right? Of course, some students just jump into the courses they like, and they may have problem because of the violation of the constraints. In this case, it's about the prerequisites. Okay, so that is the motivation. So that said, we have a set of events together with the constraints that we can represent at a directed graph. In this situation, it has to be directed a cyclic graph, meaning you don't have any cycle, right? So of course, you don't have cycle when we deal with prereqs of courses, okay? Cannot have any cycle. Similarly, for dressing up, you cannot have any cycle in there. So that is what we call the directed acyclic graph. Okay, so let me go back here. Okay. You clear about the problem we are trying to solve? Okay, so that said, we want to sort the item, right? We sort the items. Like we have a list of items that we have from left to right, okay? We want to sort the list. So there are a couple of algorithms that we can design. Okay? And of course, the easiest or the naive approach is that we just have the exhaustive search. Okay, What does it mean with exhaustive search in this situation? Again, let me pull up the example I have. Okay, so for example, in this situation, we have a set of causes together with the prereq constraints, right? So how can we find a solution that is a list of causes so that we can write down the list? For example, first semester, for the freshman, first semester, the student have to take 143, and then after that, take 311, etc. Right? So how can we find such a solution? And then freshman year, first semester, second semester, sophomore year, first semester, second semester, etc. How can we find such a solution? If we, let's say at this point, the easiest way is exhaustive search. Okay, it's very basic, but you will find out that exhaustive search is never a solution for computer scientists, right? Because of the complexity issue, meaning the algorithm in that we use exhaustive search will take a long time and consume a lot of memory space. And that's why we always try to avoid the exhaustive search. But anyway, if we want to find out an exhaustive search for this situation, what would we do? What would we do if we want to use exhaustive search? Exhaustive search means that we have to check all possibilities, right? So for example, in this case, yeah. Okay. So in that said, here is one simple example. Let me use this so we can illustrate the idea. So for example, we have the following graph, okay, 2, 4, and 3, 1, right? And then from here we have 5. Okay, so that's it. We have 5 events and constraints, 1, 2, 3, 4 constraints, right? We check all possibilities. That is number 1, 1, 2, 3, 4, 5. Okay. We list this one out. And then we check to see if there is any violation of the constraints, right? 1, 2, we have a violation right here, right? So 2 has to be on the left of 1. It's a violation. So we know that this one will not work. So, and then we check the second case, right? For example, we have 1, 3, 2, 4, 5, etc. Right? So in this case, we have 5 events. So how many possibilities we have to check? If we have 5 events, how many possibilities of the list with 5 elements we have? 5 factorial, very good. Okay, so we have 5 factorial of them. So if a graph in the real world, you will see that a graph, for example, for the network connection or for the social uh, network systems. Okay. By the way, next time I will cover some advanced algorithms in that we have to deal with graph with a huge number of vertices using the algorithm invented by Google, right? Namely the PageRank. So how can we use PageRank? PageRank for, say, discovering some knowledge from large graph, okay, is what we will learn next. But that said, 5 factorial, or if we have, usually we have about 50 courses for a program, right? And some of them are electives. Then if you have to check 50 factorial, it's a huge number, right? Uh, then the algorithm is that we have to check through 50 factorial possibilities against all of the constraints is a non-brainer, right? So that's why we cannot simply use exhaustive search, because exhaustive search will not help us to find a solution that is accepted by the users. Yeah? So we are developing softwares and programs in general for the users, not for ourselves. Of course, we need some algorithm, we need some programs, but as a software developer, we develop the software for the other users. And if the software we are developing are so slow and require so many memory space, nobody wants to have it. Okay? Nobody. Okay. So that's why in this class, I will go through some different algorithm design approaches, and we will try to see which one is the optimal or the best one. Okay. All right. So now let's go back. Okay, so we want to do some graph algorithm for solving our problem. Okay. So let's see what we do, what we can do. So let me remind you some facts and also basically the data structures and the fundamental algorithms for graphs that you already learned in the data structure CMPS 390. Okay, but you may, I mean, some of you may need to be reminded. So that's why I will remind you here. Okay, so graphs, everybody know, right? So for example, we have a graph here. Okay, a graph can be used for solving many different real-world applications. We already know that, right? For example, networks and routing, state diagram, etc. Okay, so we have directed graph or undirected graph, meaning that we don't have the direction, right? So we have vertices, edges, and for a graph, we know how many vertices we have, how many edges we have. Okay, it's trivial, right? So now, adjacent vertices and the one that is connected with the node or the vertex we are dealing with, right? And then a simple path is a path that has no repetition of any of the vertices, right? A cycle is a path in that we go back to one of the vertex, or maybe more than one of the vertices. So in order to represent a graph on the memory of the computer, there are two different ways, as you may know, right? So what are they? If you still remember. And the advantages and disadvantages of those different approaches. Let's see what we have here. Okay. Anyone who can type in a message that how can I represent a graph on the computer? Can you hear it? We have a graph, right? Before we can have our algorithm running, we need to represent this graph on the memory of the computer. How can we do that? Remember that on the computer we have what? Variable array, right? Data structure. Yeah, we can use a linked list, right? Okay. And we can also use array, two-dimensional arrays. Okay, so here is what we have. Okay, so if we have a graph like what I shared with you on the screen, right? So we have vertices 0, 1, 2, 3, 4, and the edges, for example, from 0 to 1, then we can use what we call the adjacency matrix, or in other words, two-dimensional array. So if we have an edge from 0 to 1, we just have yes or true in the cell where we have row 0 and column 1, right? Saying that there's an edge from 0 to 1. Similarly, we have 1 at the cells where we have an edge from, say, row A to column B, right? Okay. And then the other one is what we call, the other approach is what we call adjacency list, meaning we have the pointers starting, for example, node 0. From 0, we have 2 edges. Then we have a linked list from 0 to 1, and then from 1 to 4. Okay, saying that the neighbors of node 0 or vertex 0 are 1 and 4, etc. Okay, so that is what we have for representation of a graph. So you can see the difference between these two approaches are that for the adjacency matrix is easier and faster to know which, say, neighbors we have for a vertex, right? So what are the adjacent vertices of a vertex? It's easy to find. We just have to access to the cells on the two-dimensional array, right? For the adjacency list, we have to follow the pointers. It's a little bit slower. However, we still need to have that data structure, because if the matrix is too big, Or in other words, if the graph has so many vertices and edges, then we may not have enough memory space for the adjacency matrix, right? So in that case, you will see that if the user try to run our program with a huge graph, then the program will crash, right? Because it cannot find enough memory space for the adjacency matrix. So that's why nowadays, even though the memory of our computers are huge, right, like 32 gigabytes, but for real world applications, we still need to have the adjacency list, okay? Because you know that for the computer networks, we have billion nodes on the world. And with that billion nodes, there's no way we can use adjacency matrix. Okay, similarly for the undirected graph, for example, the S from 0 to 4, it means that we have two connections from 0 to 4 and from 4 back to 0. So in that situation, you have the adjacency list. In that, we have the mirror along the, say, main diagonal, right? Okay. So in terms of memory space, adjacency matrix requires big O, say n square, where n is the number of vertices, right? And then for the adjacency list, we just need to have the number of edges plus with the number of vertices. Okay, so in the real world application, the number of edges is much smaller than the number of vertices square. So that's why usually if we use adjacency list, we save a lot of memory space. Okay, but say the disadvantages are say it takes time, okay, because following the pointers is slow. Okay, so I have here for the abstract data type and also for graph traversal, yeah. But we don't need this algorithm. We just need to have the depth first search. Okay, so the depth first search is as follows. Yeah. Let me remind you here. I'm pretty sure you learned that in data structures, but I will remind you about the algorithm a little bit because we need this algorithm for the topological sort. Let me use the same example we have on the shared document so I can go through the algorithm. Okay, I will write this one down and then we will stop sharing. Okay, we have A, C first, then B, E, F, and then we have D and A. We have an H here, and then B to C, yeah, and then C to E, C to F, D, B to D, D to E, and D to F. Okay, let's see what we have is all right. Okay, so the algorithm will work as follows. Let me stop sharing. Okay, So now here we have the directed graph, right? By the way, you can check if this has a cycle. So a cycle means that if you go in one path, then you will go back to the original vertex. So in this case, you don't have from C, right? From B, you don't have it, okay? From E, same thing. F, same thing. D, same thing. A, you don't have it, right? Okay, so it means that this one is a dark algorithm, a dark graph, okay? Directed acyclic graph. Okay, so now the algorithm for depth first search will work with any directed and undirected graph. But here we just pay attention to a directed graph, and it happens to be a dark graph as well. But the algorithm will work even with a non-dark graph. Okay, so I will remove this one because the algorithm will work for a non-dark graph as well. Okay. So the algorithm will start with a coloring on of the node white. Okay, so we choose three color: white, gray, and black to color the nodes. Okay, and at the beginning we color all of them white, and we have a few things for each of the node. Okay, for each of the node we will use three variables. So we have the parent. Okay, the parent will set at known at the starting time, right? And then we have the discovery time and the finishing time for all of the node. So same thing for the other nodes. Okay, so we keep track of what is the parent of a node. When we do the depth first search, what is the discovery time and what is the finishing time of the node. Okay, so that's it. After we color all of the nodes to white and then set the parent of all of the node to none, right? So I will write here. Okay, and then we have to fill out what is the discovery time, what is the finishing time for all of the nodes. Okay. Now we can start with any node. Okay. So here the graph at the beginning, right? So every nodes are white. So that said, we can start with any node because every nodes are white. So we can start with any of them. For example, I can start with E, okay, or B here, okay, either way. So maybe I will start with B first, and then we'll ask you to do the same thing. But everybody should start with E for the hands-on exercise. So now we have B first to consider, right? So the first thing we do is that we will keep track of the nodes that we are working on by using a stack. So first we deal with B, right? And we here, I mark it. The dot here means I change the color from white to gray, saying that I'm working with the node B. So I will push it here, B. Okay? So from here, I will try to discover or try to find out what are the neighbors or the adjacent nodes. Okay, so in this case, I have C and D. right? They are both white. Okay, so that said, when we have B positive here, is the first node we are working with. So we will keep a timer. Okay, so at the beginning, the timer will be 0, and when we touch the node B, we increase it by 1, meaning that the first time we are working with B is 1, right? So at the beginning, we have timer is 0, and every time we discover a node, we increase by 1, increase by 1, increase it by 1. So the discovery time will for B will be 1. Now, next, we have 2 adjacent nodes. Which one should I use? Any, right? Because we have 2 adjacent nodes or vertices, so I can use C, right? So that said, when I decide to use C, I will change the color here from white to gray, right? And then I will push C on top of B here. And at the same time, I will record the discovery time of C now is 2, right? And also, because I go from B to C, so the pattern of C will be B, right? The pattern is B. Okay? Pattern is B, and this one is the discovery time, right? The first number is the discovery time, right? So now C is here. So we will look at the adjacent vertices of C. In this situation, we have E and F, right? So we do the same thing. We add F into this by changing the color to gray, right? Change the pattern here to C, and then the discovery time to 3. Okay? So again, we will try to look for the adjacent nodes of F. Try to look for the adjacency node of F. Okay. So F is the node we are working on. So it has no adjacent vertex, right? So here there's no outgoing edge. So that said, we finish working with the node F. In other words, we discovered the node F and check on of the vertices. It has none, so we will pop this one out, right? And at the same time, we'll say that we finish working and the finishing time is 4, right? Because the discovery time here is 3, so the next step will be the timer 4. So we have 4 here. Okay. Now, the next thing we will do is C. We pop F out, so the one on top of the stack is C, is the node we have to deal, okay? The node we have to deal with. So now, when we have C here, remember that we already used this adjacent. So the other adjacent node we have, and also we change this color to black. Yeah. After we finish it, we change it to black, meaning that we completely finish considering the node. Now, when C is here on the stack, meaning that the color of C has to be gray. Okay? We look for other adjacent nodes that is white, right? So this one is white. So we will try to discover that. When we discover that, we push it here on top of C, right? Change the parent to C, change the discovery time to what? The latest timer is 4, so this one will be 5, right? And now we look for the adjacent vertex of E that is white, right? We don't have anything. Okay? We don't have anything. So that said, we are finished working with this. So we will change the color to black. Okay? Yeah. So when we change the color to black, we are finishing the node E. So we will have it here 6 and pop it out of the working stack. So similarly, okay, after we finish this one, we go back to C, right? C has no more adjacent nodes that we need to discover. So we are done with that. So we pop it out. Right? At the same time, we try to mark this one black. And then we have here 7 at the finishing time, right? Okay, so now we go back to B. Okay. B has one more adjacent node. In this situation, we have it D, right? We push D here. The parent now is changed to B, right? The discovery time now will be 8, right? Because the last timer is 7, so now we have 8. Now from here, we change the color to gray. When we change the color to gray, we will try to discover the adjacent vertices of D. Okay? They do have E and F as the adjacent, but these nodes have been discovered already. So we don't rediscover them anymore. So it means that from D, there's no more adjacent nodes that we need to discover. And hence, we finish working with the D because there's no more adjacent nodes or vertices. So we pop it out, change the color to red, and record the finishing time, right? Now is 9. Okay. Remember that you can have a timer, right? So every time you have either discovered a node or finishing a node, you increase the timer. So now the timer is 9, right? You can update the timer here. So after we finish this, okay, go back to B because B is the one on top of the stack, okay, of the working stack. So we go back to B, and from B, we have no more white adjacent nodes that have not been discovered. So hence, we try to record the finishing time. Timer is 9, now is 10, right? 9 plus 1 is 10. So we write 10 here, update the timer, right? And then change the color and pop B out. Okay. Now, we still have one more node that is white, meaning we have not been working with node A yet. So we will take care about A by change the color to gray, push it here, right? And at the same time, record the discovery time. Discovery time will be the current timer plus 1, that is 11, right? Okay. Now, A has one adjacent node, but that node has been discovered and working with already, so no more, right? So that's why we will try to finish working with A by popping it out, and at the same time record the finishing time. Now it's 11 plus 1, that is 12, right? Okay, so here we change the color to black, right? Okay, I use the red one instead of black to differentiate the color. Okay? If I use black, it's a little bit harder to see. Okay, so that's it. We have no more node that is white, so the algorithm will finish here. So at the end of the algorithm, we have for every node a discovery time, a finishing time, and the parent. So node B has no parent, node A has no parent. Okay? Parent means that there's an edge from that parent node to the current node. But A here has no parent, B has no parent, but C has D as the parent, okay? And E has C as the parent, etc. Okay? Depending on the order of the nodes we use, like before I said that from B, we have 2 nodes as the adjacent nodes, right? If we go with C first, the parent of E will be different. But if we go with D first, the parent of E will be D, right? Depending on the nodes we choose next when we push it in the working stack. Okay, so at the end, we have this kind of information, right? For every node, we have discovery time, finishing time. Okay. That's all we need for topological sort. Okay. We don't need the parent, even though the parent will be helpful for other algorithms, but for topological sort, we don't need this information. Okay. That is the depth first search. The depth first search will help us to say going through all of the vertices in the depth first manner. And you also know that we have the breadth first search as well, right? So in that case, we don't go depth first, but we go with all of the adjacent nodes first, right? So it means that we go breadth first, but we don't use breadth first here, so that's why I will not remind you about breadth first. For example, here from one node, we have the following graph. Then depth first means we go there first, that backtrack, right? And then backtrack, and then depth first, right? Backtrack, depth first. But if we go breadth first, means we start with this one, and then all of the vertices, that is the adjacent to this one, right? And then after that, we will go with all of the nodes that is adjacent to this, and then all of the nodes adjacent to this. Okay, so we go breadth first, okay, instead of depth first, like we did here. So those are the 2 fundamental algorithms for graph. Okay. Any questions so far? No question? Okay, sounds good. Now it's your turn. Okay, so you will have to follow the same algorithm for our graph that we need to perform the topological sort. Let me have the graph here, and we'll ask you to run the depth first search. Okay, we have socks, and then short, and then pen. Okay, and we have shirt, and tie, and from pen we have shoes and bell, and from here we have the watch is okay. So here is a directed acyclic graph. Okay, so run the DFS algorithm on this graph and tell me what you have about the pattern discovery and finishing times. Yeah, so I'll give you, say, maybe 3 minutes, yeah, to see if you can finish that. Okay, 3 minutes to record the information needed for this graph. Uh, Caleb, you can start with any, okay? For this graph, you can start with any node. Oops. Okay, maybe I'll give you 2 more minutes. Once you are done, just type in each node. For example, socks. What is the discovery time, finishing time, right? For example, you have socks, and then you have 2, 5, for example, and then short, right? So, etc. Okay, very good. All right, very good. So you all start with the socks. Okay, that's right, right? Okay. But by the way, as I said before, try to finish this graph with E as the beginning node, as an exercise for you at home. Okay, so when you have this graph, if you start with E first, then what will you have? And you will see that the results may be a little bit different. Yeah. But later on, we will try to show that regardless of whatever vertex you start with, the topological sort is always correct, meaning there will be no violation of the constraints. Okay, so let me go through the solution real quick, and then we will see what kind of results we have. Yeah. So, for example, here you three of you start with the solve, right? We have the discovery time is 1, right? Okay, the parent is empty, right? And then we go here, right? And then we have 2, parent is socks, right? So, etc. I will not write down the parent, yeah, because we don't need the parent for the topological sort. So we have 1, 2, and then we have 3. And for example, I have here 4, right? No more. 5, go back, right? 6, no more. 7, go back. 8, right? No more, go back 9. No more, go back 10, right? And now we can start here, 11. Okay. Okay. Here we already discovered. So from here we have 12. No more, white adjacent, 13, 14. And now here we have 15, no adjacent node, which is 1. So we have 16 here. Okay. So that's it. We have here the discovery time and finishing time, right? Okay. So looks like you all have a solution. And now just write down the node you have. In that we have the finishing time in descending order. Okay, write it down for what you have. For example, here I have the finishing time. I have the biggest one is 16. So I will have watch. Okay, and then I will have the next one will be 14, right? Okay, shirt. And the next one will be tie. The next one I have is sock. And then short. And then pants, right? And belt. And finally, I have shoe. Okay, so here is the list I have by writing down the note with respect to the finishing time in descending order. Okay. 1, 2, 3, right? 4, 5, 6, and then I have 7 and 8, right? Okay. And I say that this is the solution. This is the solution for topological sort. And if you can check, okay, after you write down your solution, right, you check to see if any of the constraint here is violated. For example, I want to see whether or not this one is violated. Shirt has to be on the left of pants. Okay, shirt, pants, shirt on the left of pants, right? So say pants to belt. Okay, belt here, and pants is on the left of that. So meaning there's no violation. Okay, is the solution? I mean, is the algorithm simple? Yes, it's simple, right? Remember that before we have to, if we use exhaustive search, we have to consider all possibility. In this case, we have 1, 2, 3, 4, 5, 6, 7, 8 factorial possibilities, right? But here we just have to scan the nodes using DFS. And you know what is the complexity of DFS? Big O, number of vertices plus number of edges, right? Okay, so that is the complexity of DFS. So basically it's at most n squared, where n is the number of vertices, instead of n factorial, right? Which is an exponential number. So after we have the discovery time and the finishing time, we just list the nodes on the vertices with respect to the finishing time in descending order, right? Okay. Any question about this? Any question about this algorithm? Okay, and don't forget to finish this one with E as a starting point, right? And you will see that whether or not we choose E or we choose B as a starting point, you can write down the topological sort, and we still have no violation of the constraint. Okay? The algorithm is simple, but of course, we are interested in what? Number one, the complexity, right? The complexity here is simple, right? Because we already have the DFS that is big O n, where n is the number of vertices plus the number of edges, right? And then listing them simply have at most n log n, right? So in the total is still big O n squared, where n is a number of vertices. We may have up to n squared edges if the graph has n vertices, right? And here we have the list in descending order, right? Sorting a list, like at most n log n, as we all know. Now, it's one thing about the complexity, and the other thing we are interested in is how about the correctness? Is the algorithm correct? Meaning, I run the algorithm here starting from source. But what will happen, I started from tens. And will I still have the result that does not violate any constraints? That's why I asked you to run this algorithm again, starting from E, right? Yeah. And you will see whether or not the result is still correct, right? Okay. Also in this situation, instead of sort, what will happen if I run the algorithm DFS starting from the pans? Okay? So in that situation, whether or not the result is still correct. So we have to prove that regardless of whatever node or vertex we start with, or in this situation from V, we have two different ways, right? And in the previous example, in the previous hands-on exercise, I go with C first. But what will happen if I start from B and go with D first? Will the result still correct? So that's it. We need to prove that regardless of what node we start with, and regardless of the order of the adjacent nodes or vertices we go with, okay, we still have the same results. That is, there is no violation of the constraint. Okay, how can we prove that? If we look at this, if we have the nodes in descending order with respect to the finishing time, right? Then what we have to do is what? If we have to do is that for every edge from U to V, okay, meaning if we discover U and then after that we discover V, then what we have to do is that we always have the finishing time of U. How can I say with the discovery, I mean, this finishing time of V? For every edge from U to V, right? When we discover U and then the color of V is white, meaning V is the next step during the discovery process, we need to show that for every edge, okay, the finishing time of U how can I compare with the finishing time of V? You have to be on the left of V on the list. What does it mean? Greater than. Very good. It has to be greater than. Right? Okay? Now, how can it happen? Here, when you discover you have you here, right? Somewhere. You may have something before that, right? And then after that, you may have something here. And now we have V here, right? So that said, the discovery time of U is from here, right? And now you have V, you discover that. But V have to be finished and pop out before you pop the U out, right? So that means the finishing time of U have to be less than the finishing time of V. I mean of U, right? Yeah. So U here, now we discover V. V has to finish first and pop out before U will be reconsidered and then finished. Right? So that's it. For every edge U to V, you have the finishing time of U is bigger than the finishing time of V because it's after you finish the U, pop it out, right? Okay, so that is the correctness of the algorithm. So any edge U to V, we will have the property that the finishing time of U is greater than the finishing time of V. Okay, so that is the basic for the correctness. And I already posted the write down for the correctness of the algorithm on Moodle, right? And lecture notes are also posted. Okay, so any question? All right, so I saw that some of you already submitted the homework assignment too. That's good, right? But next time we will learn one more advanced algorithm for the graph. But everything up to today will be covered in test number 2. Okay? So if you have any question or if you need me to do one more hands-on exercise on any topic for test number 2, just send me a message and then I will do it on Tuesday before the test on Thursday. Okay? That's it for today and take care and bye-bye.